I would like to introduce our awesome speakers. Today we have here Kenneth Wyatt. He's our guest speaker. And we have Anana Awasi, who is our product manager here at Astrodyne TDI. Kenneth is a principal EMC consultant at Wyatt Technical Services. He has worked in the field of EMC engineering for over 30 years with a specialty in EMI troubleshooting and pre-compliance testing. Kenneth is widely published and recently completed and released his third volume for his book, EMC Troubleshooting Trilogy, which is now available through Amazon. Anand, like I said, is our Director of Product Management for the EMI Filter Division here at Astrodyne TDI. He has over 30 years of collective experience in the EMC industry, 20 of them with Astrodyne TDI. His main role here at Astrodyne is to support partners and customers through the EMI filter selection process and provide knowledgeable insight to improve equipment performance. If you have any questions throughout the training, please make sure to drop all the questions in our Q&A box. I'll try to keep an eye on it and try to bring up the questions as I see fit. And also, I will like to disclose that for the trivia, we will be selecting a winner that is not part of our rep program and also not part of Astrodyne TDI. So I just want to wish everyone good luck. And now to kick off the trivia, I just have a quick poll. It's 5 seconds to get people, warm up with the trivia. So here we go. How familiar are you with Astrodyne TDI's product and services? And there's no correct answer. There's no point for this question. So please answer truthfully and we'll make sure to make a note. All righty. Again, if you want to participate in our trivia, you can log in to kahoot.it and enter the game pin is 2504839 and you'll get to participate. So now I'll pass it over to our speakers to begin the training.
Oh, thank you, Monica. Welcome everyone. Good morning, good morning, and if you're in Europe, good afternoon, and welcome to this EMI Friendly Design Practices seminar that we're doing today. The intent for this is that EMI has forever been shrouded with mystery, and our intent is to clarify some of these misconceptions. So Astrodyne TDI has been helping customers solving their problems, getting them into compliance. And as a company, we've been doing this. And Ken has been doing similar efforts with certain customers and OEMs out there independently. So we have spoken about these friendly practices and how to comply, what the best practices are in past in a number of our webinars and seminars, and a lot of white papers on our website as well. But we thought it would be good to get a third party and independent perspective on the issue. And that's why Ken, being one of the experts in the area who works independently on this, we thought we'll bring him on board and have a chat with him, ask him some questions, see what he thinks about the issue, what his ideas are, and hopefully our ideas and your ideas coincide and we have the same view. So it'll be a good session for all of you to learn a little bit about what good practices are, how to design a filter, how to do a system design, and so on and so forth. So I'll start here. So to begin with, Ken, can you give our audience a general information about what emissions are and what you're going to talk about today?
Sure, and thanks, Astrodyne TDI for hosting this. So the main emissions issues in a product are generally radiated and conducted, and we'll be focusing mostly on the conducted emissions in this presentation. So it's all about power line filters. And, electronic products these days tend to produce a lot of emissions due to the digital circuitry and the switching that's going on, especially in power supplies. So we need to be good citizens and reduce the harmonic emissions that products can produce so that they don't interfere with other products or existing communication systems, for example.
Yeah, sure, Ken. Yeah, and the switching speed and the clock speed has been going up and up, and it's becoming more and more of an issue, with especially the electronics getting more and more power. So the noise being generated is a lot potent than what it used to be 20 years back. So absolutely. We might touch a little bit on radiated as well, Ken, as you will go forward, I think, because as when you and I were talking previously, conductor and radiator do go hand in hand a little bit. So we will focus on conductor, but you can never say no to radiator because always things get radiated. So moving from there, so emissions can create a lot of, we understand, that they can create a lot of operational issues. And if there is a noise in the system, you could see, the user interface might not be working properly. One subsystem may not be talking properly to the other one, or if you're in an industrial setting, let's say, one system could be interfering with the other system. So we have seen those, and sometimes a filter is needed for those. But if those are not an issue for a designer, what would be the concern or the reason that a customer or a designer will need to worry about EMI?
Well, probably the most prominent issue is, as you mentioned, radiated emissions. Now, this particular slide showing now is the FCC Class A and B limits for conducted emissions. Now, conducted emissions are those noise currents that are coming out the power line or the mains wiring, and so we like to minimize the harmonic content coming out the power line. And for the most part, these conducted emissions are due to the switch mode power supplies that we tend to be using these days for efficiency reasons. And you can see most products, including military and aerospace, do have limits on conducted emissions, and as well as medical products. Pretty much all products that have digital circuitry are required to meet some sort of limits for conducted emissions.
Sure, yeah, that's a good point. And what we realize is when you're talking about military, DO 160 or medical, no matter where you are in the world, globally, compliance to emissions is necessary, it's mandatory. But for the benefit of our US based designers, there are applications in the US that are kind of exempt from emissions requirements. One of them being appliances, household appliances. But again, there have been instances where OEMs have put filters on their circuitry because it's not because of the compliances, it's because of the noise issue, that it was generating so much noise that they had to put it because it was not able to function properly, or it was becoming a bad citizen, if you will. So the point is, you either need filtering because you need to keep the noise down so that it becomes a good citizen, or sometimes you have to put the filter because you have to comply to a conducted emissions requirement set by certain agency standard. In both cases, what you're trying to do is you're trying to basically stop the noise within the unit before it goes out and either makes you fail or contaminate the other equipment in the area and doesn't allow them to function properly. So no matter what side you're coming from, you're trying to do the exact same thing. So now that we know what the emissions requirements are and why somebody needs to comply to these emissions requirements or need to have a filter, what's a typical remedy that you suggest to your customers? And what's a typical topology design, EMI filter topology, if you will, that helps them?
Yeah, and before we get to the topology, we do have 2 quick trivia questions. So get your phone out, make sure you're logged into kahoot.it and enter the game pin. And this will be our first question with points. What type of emission can affect EMC compliance? Only radiated, only conducted, carbon dioxide, or conducted and radiated? right, so everyone got that question right. And
Right.
just to let you know that speed is part of the game. So not only answering correctly, but also the speed in which you answer, you'll get more points. So Tiago, good job. You're in the lead now.
We've got a pretty smart set of audience though. Everybody got it right. That's great.
Yeah. Next question is, electricity is energy caused by the flow of what? Power, energy, electric charge, or force? All right, and the correct answer is electric charge. Most people did get it correctly, so that is good. Oh, BMAC, Tiago, and Tiago Nunes. All righty, and back to the topology. There we go.
So this is a general basic topology for a power line filter. And what's interesting is that these power line filters filter both differential mode and common mode noise currents. The differential mode, what we'll be talking more about in the next slide, but the differential mode is due to the switching action of the switch mode power supply. And it turns out that the X capacitor and the common mode choke in a differential mode inductance acts as filtering for the differential mode currents, noise currents. And then the common mode part of the filter includes the Y capacitors as well as the common mode choke. So what's interesting is that common mode choke is part of both kinds of filtering. And we'll talk more about that in the next couple slides.
So now that we know that there are common mode and differential mode kind of filtering, I think it might be pertinent to explain what these different noises are, how to differentiate between them, how to categorize them, separately measure them, and what a typical circuit element, how a typical circuit element will mitigate these.
Mm. Yeah, that's a great question. And it turns out that the differential mode current is the signal current or the power current that's flowing in your circuit. And this is as you can see in the slide, this is it's the main current that is switched in the switching power supply part of it. The common mode current is the kind of noise currents that we don't want, and it is largely generated by parasitic couplings and things like ground bounce in your ground return path, and we'll talk about that in the next slide. But here we see the parts of the differential mode filter that are enhanced in a magenta color. And so you see the X capacitor in combination with the common mode choke is filtering the differential mode noise currents that are occurring due to the switching action. And so we see the differential mode noise is reduced by the time it comes out at the power input. Now the next slide.
So before we go to the next slide, Ken, I think, can you go back, Monica, a little bit? I just wanted to point out something.
There we go.
Anyway, so I think what I see here is that differential mode noise, and maybe this will be of importance to our audience. A differential mode noise typically is not present on both the lines. It's not uniformly present on both the lines. It's either line or there's a different signal present on each line. That's one thing I think what you're trying to point out here, right?
Right. Yeah, it's the main current that operates your circuit basically.
Got it. Okay, so it's basically an imbalanced sort of noise. It's not that symmetrically present on both lines. And that you pointed out about common mode, and that's a great point. Yes, we always use the imbalance in the common mode coil, or rather the two windings are never identical, and there is a percentage of difference between both the windings on a common mode coil, and that becomes a differential mode inductance, which helps the differential mode noise. But there are a couple of applications we work with, typically MIL 461 and the lighting application, where the compliance requirement goes down to 9 kilohertz, which is way below 150 kilohertz commercial frequency range. And a lot of noise in that area typically is differential mode. And capacitors do help up to 50 kilohertz, but once you go further down, what you really need is a pretty substantial differential mode coil. And a lot of times the residual inductance of a common mode is not sufficient. So you will, our audience probably have seen in past why there is a huge differential mode inductance in the circuit. That's not shown here, of course, because that's not a very common thing. But if it's there, that means you probably are trying to comply or trying to mitigate noise in a very low frequency range where the residual common mode inductance or differential part of the common mode inductance and the X capacitors are not too effective. Once you go below, let's say 50 kilohertz range, you will need large differential mode inductors, and that's another way of mitigating the differential mode noise. But that's not common in all the most commercial applications. You won't need it.
Yeah, right. So this I'm trying to show or depict the path of common mode currents. Again, common mode currents are equally split between the line and the neutral, and the Y capacitors divert this common mode noise current to earth or the chassis of the product. And those Y capacitors act in conjunction with a common mode choke to reduce the harmonic emissions due to the rise and fall time, primarily of the switching power supply. And as the MOSFET in your switching power supply switches on and off, it creates a current dip in the system, and that dip works in conjunction with inductances and the return path, and that's really one of the main things that creates this common mode noise current. And the generally speaking, the common mode noise is going to be under 100 megahertz typically. Most commercial line filters have an upper range of 30 megahertz to, some military filters might go up to 100 megahertz or higher. And so these frequencies that are below 30 or 100 megahertz are generally common mode. And you can see that the common mode currents can flow in your chassis or your ground structure, as well as the wiring in your power supply and filtering. And so you can see that the Y capacitors divert that to chassis back to the source, and the common mode choke helps block the common mode noise currents from getting out the power line or the mains input. Did you have anything else to add, Anand?
Yeah, I think this is great. Yeah, I think what you're showing here is that the common mode noise is present on both lines with respect to ground. So it's a very symmetrical noise in both line and neutral. I do have a question. So if you have a Y capacitors that are bypassing the noise coming from inside, why do you need a common mode coil?
Why do I need a what?
A common mode coil.
Oh, well, the capacitors act as a diversion back to the source, which generally is earth ground. The common mode choke is a blocking element, and so between diverting the noise currents and blocking the noise currents, they work hand in hand.
Got it. Okay. Thanks for explaining that. Appreciate it. Yeah. Okay. Great. So yeah. So I think we have seen it. We have looked at the single phase topology, and there are, I mean, sure, there are people in the audience who have worked on three-phase systems and have seen three-phase filtering, and must be wondering how that equates to a three-phase single phase topology. Works with three-phase system. So here's a simple filter topology of a three-phase filter, and you've shown how the X capacitors and Y capacitors are placed. In general, if you look at a very simple three-phase filter circuit, you will see the X capacitors are connected between the phases. So you'll have one between phase A and B, one between phase B and C, and then the third one will be between C and A. And all the Y caps will be connected from each of the phases to ground. So you'll have three Y caps. And that's perfectly right. So that's exactly how you derive it from a single phase. However, what we have seen in past that tweaking the circuit a little bit helps a lot, both in the EMI mitigation and the component selection and leakage. For example, rather than connecting our X caps between the phases, what we do is we try to connect them together like a star at a neutral point. So now what you're doing is your capacitor doesn't have to really withstand all 480 volts if you're using a 480 volt system or power. Your capacitor doesn't have to withstand 480 volts. You can get away using a low voltage capacitor because between two phases, if you see in the circuit, there are two capacitors in series between two phases. So you can get away with a 300 volt rated capacitor and still withstand 480 volts. So you can go to a smaller, cheaper component. You're still using three capacitors, not six, because otherwise, if you want to use 300 volt rated capacitors between the phases, you have to use them in series. So you use 6 of those. You're still using 3. However, you are able to put them in series and get all 480 volts across them. The other thing is you can use the neutral point as a point to connect to ground. Like you don't have to put your Y capacitors from each phase to the ground. You can put the Y capacitor between neutral point to the ground. The good part about that is why we do that is, first of all, neutral point typically stays at a zero potential if all your three phases are balanced, which means there will be barely any leakage current flowing. So you will really reduce your leakage current a lot compared to connecting your Y caps from phase to ground. And if, let's say, there is an imbalance and there is some voltage, it will be nowhere close to the line voltage. So your leakage current will still be very low. But this Y capacitor will still work at bypassing all your noise down to the ground. So you achieve both. You get the common mode performance of the Y cap, but you don't get the same leakage that you'll get in a typical three-phase system where the Y caps are connected between line and the ground.
Thank you, Anand. And then on that note, we do have 2 more trivia questions coming up. So get your phones ready. And again, kahoot.it, and the game pin is at the bottom of the screen. So the first question, double points. What are the types of noise? Common mode, diameter mode, correction mode, or differential mode. And this is a multi-select. So make sure you select multiple answers before submitting. Good luck. Right. Looks like there was a little bit longer time. So oh, awesome. Okay.
I think they nailed that one.
Yeah. All right, Tiago's still on the lead. All right, the next question is a multi-select, once again, for double points. What do you need to know to select an EMI filter? The attenuation requirements, amperage ratings, filter style, filter brand. Make sure you are selecting multiple answers, and again, good luck. Right, so 3 people select the wrong answer. You don't need the filter to know the filter brand during your filter selection, unless you're selecting an Astrodyne EMI filter. All right, next, I'll pass it. Okay, we have Tiago still on the lead. Wow, very good. up 5 places. Dave E. That's awesome.
I see a question on the panel here. Before we move on, might want to answer that one.
Will there be significant reduction in noise between the delta or star configuration in XCAP? As long as the overall combined capacitance between the two phases is same, there will not be any impact. We say the star configuration is better because you are able to use low voltage capacitors, so it saves you some cost. These are smaller and still using 3 of those. And again, it allows you to connect your Y capacitors from neutral point to ground. Hope that answers the question.
All right. So
yeah, so we talked about common mode and differential mode. You gave a lot of information on that, Ken. So now, I guess the next obvious question is, well, there are 2 types of noises. Is there a way to measure them? Is there a way to categorize them?
right. And if you can measure them separately, that's a real advantage because it'll help you select the appropriate attenuation for the filter. So because the line filter is designed to reduce both differential and common mode noise currents, again, it's a good idea to be able to separate these noise currents and actually measure them. And that way you'll be able to specify the appropriate attenuation based on which mode is higher and at what frequencies. So in the left picture, stringing the power input wires through an RF current probe, that will measure the common mode noise currents. On the right-hand side, reversing one of the power input wires backwards through the RF current probe will measure twice the differential mode currents. So I don't know if you're familiar with RF current probes, but they are designed to measure the very minute RF harmonic currents in a wire or cable. And most of these current probes will measure up to 200 or 500 or even higher megahertz. And they are designed to measure microamps of current. And so they're very useful for assessing the conducted emissions that are coming out the mains cables or any wire really. They're very helpful as well in measuring or evaluating radiated emissions because it happens to be wires or cables that act as good antennas and can transmit these harmonic emissions through the air.
So, if someone doesn't have an access to, let's say, these probes and using listens, is there any way to do the same kind of measurement using listens?
Good question. Yes, in fact, my book on troubleshooting EMC, the volume 2, I talk about both radiated and conducted emissions. And it turns out that you can use a regular clamp-on ferrite choke, wind a few turns on 1/2 of it, and use that to measure RF currents in wires or cables. It's a kind of a do-it-yourself current probe. It works pretty well. It's just not calibrated.
Cheat trick, huh?
RF current probes. But yeah, that's and in fact, I'll talk about that during one of the case studies.
Cool.
So one other way to measure or separate out the differential and common mode harmonic noise currents is to use something called a listen mate. This is being marketed by a company called TechBox, and you use a pair of line impedance stabilization networks or listens, LISM, and this in combination with the listen mate. And the listen mate has ports for separating out the common mode and differential mode noise currents. And as you can see on the screen capture on the right, we see the differential mode noise current as highest. So we need to ensure that whatever filter we select has a high differential mode attenuation in that frequency range, which is roughly 10 kilohertz to 15 megahertz. And so you can look at the various attenuation curves, and that will help you select the appropriate filter for this particular noise that you're measuring.
This is very useful, Ken, because a lot of times we get these test data from our customers and they show they fail. There's one plot, there's an average plot, there's a quasi-peak plot, and they fail, and the limit lines, they fail. Now, nobody cares to find out if it's differential mode or common mode noise that they're failing on, and then they try a filter, and sometimes it works, sometimes it doesn't, and then say, oh, it's a black magic. No, it's not black magic. If you decipher it correctly, it's not black magic. And but if you have this kind of breakdown available, Monica, can you go to the next slide? Most filters come with these kind of plots or a table which clearly specify the common mode and differential mode performance of a filter. So if you can break down your noise appropriately, even if you're failing on a higher frequency, if your noise is predominantly differential mode, that's what you're looking for. You're not looking for a common mode filter. And even if you're failing in a low frequency, if your noise is predominantly common mode, that's what you're looking for. So it really helps you pick the right filter based on the noise footprint of each individual type of noise. So we definitely would encourage our audience here to try and get that information. When they fail in the frequency range, it's much easier to get it done quickly and see what type of noise they are dealing with. It could be both, but once you know what it is, it's much easier for you to go and select the right filter for the application.
Basically, if you can measure it, you can fix it.
Absolutely.
And, not too many people, there's a question here in the Q&A panel. Does the common mode and differential mode noise aggregate constructively? Often EMC tests do not break out the two noise sources at the test center, and that's very true. It probably depends on the phase of between the common mode and differential mode as to whether they constructively add or subtract. What you measure during the conducted emissions test is an aggregate of both. And so you really don't know which is the higher, the differential mode or the common mode. So it's really nice to be able to separate out between the two, and that'll be a great help in selecting the right filter.
Yeah, and most labs will not measure it because the standards don't call out for common mode or differential mode, just call out for noise. So it's onus is on us to figure out what it is and then break it down in a way that it helps us select the right filter. And yes, they do aggregate, but I believe they don't aggregate linearly, right? They kind of it's a complex addition. So 6 dB of each will not probably turn into 12 dBs, but it'll be something in between. So now that we have figured out how to understand common mode differential mode noise and how to find a filter. Now, what are some of the do's and don'ts? Like how to select a filter, but now you're putting a filter in a system. Sometimes you have the right filter, but depending on how you put the filter in a system could also be detrimental. You don't put the filter the right way, the good filter is not going to work for you. That's what we have learned. So can you throw a little bit of light on what it is? What are the typical do's and don'ts of putting a filter in the system, how to install them, what the best practices are?
Well, here's an example. A lot of filters are wired into the circuit, and we want to make sure that the wiring between the filter and the mains are short as possible, so that they don't tend to couple other noise sources within your circuitry. And some of the case studies will show you why that's a bad idea to have long wires between where the mains input is and the filter, because you've got a quiet side on the mains side and a noisy side on the circuit side, and we don't want all that noise from the circuit side to bypass the filter. And so we want to, in the top photo there, we want to minimize the length of the wires between the filter and the mains input. And ideally, by using a bulkhead mount filter, which attaches directly to the back panel, for example, that is ideal because now you've eliminated the wires that could potentially pick up or couple noise bypassing the filter.
This is interesting, Ken, because, in the first slide, you're talking about, conductor and varied that go hand in hand. This is a typical example where you're trying to clean the conducted emissions, but because you have long wires on both the sides, and now I tend to, go in the air, radiate, and couple back on the other side. So that's what we're talking about when you say conducted and radiated go hand in hand. Now, there'll be instances where somebody will not be able to put a bulkhead mount filter. Either it's a hardware unit, or they don't have space to put a bulkhead mount filter, or they have to live with something which is a unfiltered IEC or something like that. So what are the typical good practices to follow there?
Okay. Additional practices will be after the next trivia question. So we do have a trivia question coming up. It's another double point. A ferrite choke is always necessary to reduce emissions. True or false? All right, a couple more seconds. Okay, so the correct answer is false. Do you want to clarify that one, Anand?
Yeah, it's not always necessary. Sometimes it does become necessary, but not always.
Yep. All right, Tiago still on the lead. And Pete just stepped up a couple spots, so good luck. The next question is: the current is often described as being either direct current or what? Current, compact current, adjustable current, or alternating current? Ooh, everyone knew that one.
Everybody
Maybe that
electrical
one was too
engineering. That's
easy.
good.
Wow. Tiago hasn't lost
Good,
his
Tiago.
butt.
There you go.
Good luck. All right. Next, getting to some more examples.
So sometimes a ferrite choke is helpful, and it has to do with the fact that most power line filters are designed with an upper limit on frequency. And I mentioned earlier that upper limit for commercial line filters is usually 30 megahertz. For military or aerospace filters, it can be much higher. But the fact is, the conducted and radiated emissions kind of go hand in hand, and there's kind of a blurry difference between the two as far as where's that where do conducted emissions fall and versus radiated emissions. And so if you're using a power line filter that has an upper design limit of 30 megahertz, it could attenuate higher than that, but we don't really know because it hasn't been measured. And so sometimes a ferrite choke is added to the input wiring on the filter to help reduce the radiated emissions that might be leaking through the power line filter. And so that's what we're indicating here on this slide. Do you have anything else to add?
Frequencies, yeah, no, this is good. I think this also answers the question I was asking you before the last slide, I believe. So if you cannot put really a filtered inlet at the chassis level and you have wires on both sides, sometimes putting a ferrite bead could help you achieve the same goal that you will achieve by putting a bulkhead mount filter. Now,
I've seen this issue more than once as I'm helping clients. And what they tend to do is that they want to make the wiring look neat. And so they'll take the input wiring and the output wiring and bundle them together. And what that actually is doing is shorting out the filter at high frequencies. And so it greatly reduces the performance of the filter when you couple the input and output wiring together. When I was working for Hewlett Packard, we had a marketing department that actually developed a product for a client that we in the R&D area didn't even know about, and they had done this bundling. So we had to educate our own marketing people about filter installation practices. But yeah, this can happen. It's something that I look for when I'm working with clients.
Yeah, you're introducing the noise back to the line that you just cleaned out. That's what you do. It's a pretty it's an interesting picture here, because I used to work a lot with vacuum cleaner manufacturers. I mean, a lot of appliance manufacturers do it, but their other appliances have a lot less space, so this typically doesn't become an issue. But given the vacuum cleaners have a lot of long wires, so there is an urge among the production engineers to clean the things up. So we designed a filter, we wired everything, and we said, this is how we give them picture. And it goes into production floor and say, this is a mess, wires all over the place. You gotta make it clean. They put everything together. And of course,
right.
they go to final lab and they fail, and they say, hey, you guys developed a filter and fail. I said, no, can't. Send it back to us. And then of course, this is what we saw. All the wires were neatly bundled together. Great, housekeeping, but doesn't help in EMI. So we had to really tell them, hey, you cannot do that. You got to tell your production line people that they have to keep this input and output wires separated. It's critical.
And with that, we have another trivia questions coming up, 2 other ones. True or false? Early capacitors were also known as condensers. True or false? And the answer is true. Tiago Nines just had 7 streaks in a row. So he's coming for Tiago. Good luck. Next question. True or false? In a capacitor, energy is stored in electrostatic fields.
Electrostatic fields.
Electrostatic field. Thank you. True or false? And that is true, and most people got it correct. That's good. No, not much change, but Ben Abdi just got 3 streaks in a row. So you just have to get on the board, Ben. All right. And next.
I see we have another question in the Q&A panel. Ravindra is asking, are common mode chokes really effective when we populate them on PC board due to parasitics? My experience shows negative impact with immunity and ESD tests due to the high impedance offered by common mode chokes in the higher frequencies. I guess I'm not quite sure how to answer that. It's one of those, probably it depends on the board layout answers.
But we have to look at the entire design to see if it's going to impact or not, I guess.
Yeah. It's true that when you mount a common mode choke on a PC board, you will have capacitive and inductive coupling to it, which could impact the performance. So that's That's something that you'd have to, I think, check. Once you've got the circuit designed, you may have to move it or rotate it to prevent couplings, for example.
Right. Yeah. So that was actually a good leading question, because we have talked about the type of noises. We talked about different filtering circuits. We talked about how to understand noise, how to mitigate it. Now, I think some of the examples will really help us understand. If you can show some pictures and say what you've seen in the field, that might have pictures worth 1,000 words, as we say. So if you can show some real life examples and explain what you saw in the field and how you fixed it, that'll probably go a long way, along with all the other information that we have provided today.
So let's move on. We've got a couple of case studies to show you. This particular case study is an industrial washing machine. And it turns out that most appliances these days now use what's called a variable speed drive motor. These motors are driven by a pulse width controlled power converter, which usually produce a very wide range of harmonic noise currents. This particular case study, the client had tested a commercial washing machine and had simply tacked on a line filter with poor attenuation properties. So I was helping them to select a more appropriate filter, and after comparing the performance of this filter with a dual stage filter from Astrodyne TDI, I supplied them a sample. And the difference between their single stage filter and the dual stage filter was what was required to get them to pass. We'll see in the next slide the differences. That top chart shows the common mode and differential mode attenuation at various frequencies of the original filter. And comparing with the dual section filter, you can see a huge improvement in attenuation, and that's really what it took to get this washing machine to pass the conducted emissions. You can see the difference in the plots on the right, before and after.
Yeah, really. The failure was in the low frequency and the high frequency range, and that's where you see the major difference in the performance of both the filters. So yeah, it does make sense.
This next case study again is an appliance, and the product in this case is a commercial air conditioner. Also driven by a variable speed drive motor. These things, the drive circuitry is very noisy from an EMC point of view. And just visually inspecting the layout, we see that the line filter is too far from the mains input. There are also several parallel wires coupling directly to the mains wiring prior to the filter, and the variable speed drive circuitry is unshielded and just an open board. This arrangement coupled harmonic noise currents directly out the mains cable and included frequencies from 100 kilohertz to 300 megahertz and higher. Now this is the case where I was able to help the client construct an RF current probe using a clamp-on ferrite choke. And so I don't have a picture of it, but you simply wind a few turns around half the clamp-on choke, and then you clamp that around the mains cable and connect that to the spectrum analyzer. And we were able to use that do-it-yourself RF current probe to troubleshoot this product and get it to pass. So, it doesn't take very expensive instrumentation to help you troubleshoot EMC issues. And I talk about that, various techniques in my books. So here's the results of our rearranging all the components and moving the wiring away from the mains input wiring that connects to the line filter. We weren't able to move that line filter, but by rearranging the wiring, moving some of the components away from the mains input, we were able to reduce the coupling. And this helped the harmonic emissions below 30 megahertz. We still had to add a couple different mixes of ferrite chokes to the mains wiring to the filter, and in order to attenuate the frequencies above 30 megahertz. And this modification was enough to get the air conditioner to pass the conducted emissions. So sometimes it's been my experience that appliance manufacturers usually use a pretty haphazard wiring, and if you look inside your own washing machine or dryer, you'll see that the wires are routed just anywhere they fit. And for EMC purposes, you really have to be more careful about routing and how, what noisy wires are coupling to quiet wires. So that was the case in this point.
Yeah, don't wire for convenience, wire for EMC, better EMC. We saw a similar, this is pretty interesting picture, because we saw a similar case with one of the companies that make products for semiconductor manufacturing industry. And they have a little box, that's a control box where all the electronics comes in, all the controls are. And what they do is they have multiple OEMs and they supply these boxes. They supply 500 units to one OEM and another 500 to other. And each OEM has slightly different need. So they have to rearrange or reconfigure the control a little bit. But in the end, it's the same componentry. So the filter still passes. When the last go around, the filter failed. And they said, oh, have you guys changed the filter? No, we haven't changed the filter. It's a standard product from the catalog, can't change. So then we said, okay, can you send us some pictures? Of course. What they did is they moved the filter about 2 or 3 feet away from where, because a bigger unit, 2 feet away from where the power enters the box. And, wiring is going to the filter, coming back to the controller, and everything right next to each other. We said, why did you guys move it? Oh, because we are trying to optimize the space utilization. I said, yeah, it's convenient for you, but it's not convenient for EMC. So you might want to move the filter back to the power input side and reconfigure the system. So, sometimes what's convenient for putting the components together may not be as convenient for EMC. So keep EMC in mind before placing the components in place. It's very critical.
Looks like we have another question that we might want to answer next. Anurag asks, what are your thoughts on transformers close to fast switching MOSFETs? That's a very interesting question. And typically what I recommend is that all the components of a switching power supply should be mounted as close together as possible. And the reason is to reduce the loop areas of these currents, the drive current, the switching currents. We want to minimize the loop areas, because any loops with high frequency currents are going to start looking like an antenna and radiate. And so I guess specifically your question is about transformers close to switching FETs. I'm assuming the MOSFET is driving the transformer, and that should be as close as possible to reduce the inductive path between the MOSFET and the transformer.
Awesome. So now we have the two final questions before we close out our training today. So the next trivia question is for double points. What is a good practice to follow during EMI filter installation? Wire filters should be located close to the mains inputs. Bulkhead filters should be avoided. Filter grounding is not critical, and input and output wiring should not be cleanly bundled together. And the correct answer was wired filters should be located close to the mains inputs. So good job.
Yep.
And Dennis finally got to the top. So that is awesome.
A major disappointment.
All right, and our final question, this might be the deciding questions. Long before any knowledge of electricity existed, people were aware of shocks from what type of animal? Bees, echidnas, platypuses, or electric eels? And there is the answer there in the picture. So let's see. Oh.
Kind of gave it away there.
Yeah. Yeah, that was a little bit of help from the host there for the final question. And now, before we announce the winners, we have some resources that we will be sending out. We will be sending out a copy of the presentation as well as the recording for everyone who participated. And also, these are some resources where you can find some information about EMI filters. Kenneth was mostly collaborating with other people, and he also wrote his own books. And now he's at volume 3. So those are available through Amazon, and we'll send you the links for that. And again, we would like to thank everyone for participating. I will send both Anand and Kenneth's information over. So if you have following questions, or if you want to stick around for a couple more minutes after, I'm sure that Kenneth and Anand can answer some additional questions. And